welcome to. Yeah, anyhow. There we go. So chemistry 3111, just as a bit of a review of what we covered last class. We're not going to review everything that we covered last class, but we talked about 3 different ways that we could make a primary amine. We talked about doing the Gabriel synthesis, which is shown on the far left. That's where we take potassium phthalimide, which can be made from phthalimide, and then we just deprotonate it rather, using potassium hydroxide. Then it does an SN2 with a primary or methyl halide, and you can do it with a secondary too, I suppose. The yield might not be as high, but you do an SN2 like that. Then you treat it with hydrazine in order to produce an amine. The next one that we looked at was using sodium azide. So sodium azide, we usually write it like this, NaN3. So you know that sodium is a cation and azide is an anion. And here is the Lewis structure of the azide anion here. So you can see how that can act as a nucleophile as well. So we have our nucleophilic attack and our loss of our leaving group. And then we can reduce that azide down to the primary amine. We've got a couple of options. We can either do it with hydrogenation conditions. So that's just treating it with hydrogen and palladium, platinum, or nickel. Or we can use lithium aluminum hydride reduction followed by treatment with water to produce the primary amine. And the last one is one of my favorites, which is reductive amination, a very common reaction in organic chemistry, especially nowadays, very widely used. So what we saw is that, putting a ketone or aldehyde with an amine in a catalytic amount of acid, we know that that makes an imine. Now, if we were to put sodium borohydride in that reaction mixture, it would reduce the aldehyde or ketone, and that wouldn't give us anything. But since we mitigate the reactivity of the borohydride by using sodium cyanoborohydride, it will only reduce the imine that is produced in situ. Remember the word in situ, which means in the same reaction flask. So organic chemists love reactions where you can just combine everything in one flask. You just throw your amine, your aldehyde or ketone, a little bit of acid, so some sodium cyanoborohydride, and just like that, you have a primary amine. So 3 really cool ways of making a primary amine that we talked about in the last lecture. Then we talked about how we can use a primary amine and how we can further use reductive amination to make secondary and tertiary amines. And then we said, well, you can also do an exhaustive alkylation of a tertiary amine by treating it with an appropriate alkyl iodide. And of course, we know that an amine can behave as a base. And so we talked about that at length as well. We tried some problems, and then we moved on to acylation of amines. And this is a reaction that we looked at in detail when we talked about carboxylic acids and their derivatives, right? We talked about amides and how to make an amide. We said you take an acid chloride, you treat it with 2 equivalents of the appropriate amine, and you can make a secondary amide like is shown here. You could use ammonia, make a primary amide. You could use a secondary amide and make a secondary amine and make a tertiary amide. Anyhow, but we said the reason why you need 2 equivalents of the amine is because you produce HCl in the reaction, and the second equivalent of the amine is going to react with that HCl to make some kind of chloride salt. Okay, here it's just some kind of alkyl ammonium salt, and that removes the HCl from the reaction mixture. And we know that HCl is a strong acid, so it can be deleterious to a lot of different reactions that we might want to do. Now, we've also discussed acylation in terms of an acyl group being a protecting group of an amine. So why would you want to do that? Because we saw way back in chapter 18 that if you take an aromatic compound like aniline, it has got the amino group here, which is so strongly activating that if you just take that and treat it with bromine, no Lewis acid required, you end up with a polybromination occurring. Wow. So you end up installing all of these bromine groups. And so what would happen if you wanted to only install one bromine group para to the amine? Well, in that case, there's a strategy for that. And the way that we would do that is by protecting the amine on the aniline ring with an acyl group. So once we make it an acyl group, it's still an activator, but now it's a moderate activator, so that when we treat it with bromine, we only get monobromination. And then we can just rip that acyl group off. We just use hydrolysis. You can either treat it with sodium hydroxide, or you could treat it with aqueous acid followed by sodium hydroxide. So kind of cool. The only disadvantage of this synthesis, of course, and we discussed this at length, in the carboxylic acids chapter is that hydrolysis of an amide is just a pokey reaction. It's just slow, okay? It requires harsh conditions, and there's no way around that. Another thing that we saw was, well, if you want to do a Friedel-Crafts reaction with an amine or an aniline derivative, we said you can't do that. Why? Because the amine will act as a Lewis base and aluminum chloride, which is required for Friedel-Crafts reactions, whether it's alkylation or acylation. This is a Lewis acid, and so you get this Lewis acid base reaction here, and you end up with something that's really deactivated now. So that's not going to react towards alkylation. So what's the end run that we can do around that? Well, it must be acylation, right? And it would be 100% correct in assuming that, because that's the title of this section. So what do? We first acylate it, which serves to protect the ring. Then when you treat it with your alkyl halide and your Lewis acid, the Lewis acid isn't going to react with the lone pair on the nitrogen. Everything works out hunky-dory. You can do your Friedel-Crafts reaction, install your methyl group here, and then we're going to just remove that acyl group the same way we did a couple of slides ago. Again, pokey reaction, but hey, it works. All right. And we took a look at a couple of questions, and then we looked at Hofmann elimination, right? You remember, go all the way back to your early days of Chemistry 3101, Organic Chemistry 1. We spent a lot of time talking about Zaitsev products, right? That was the most substituted alkene that was produced by elimination. And then we talked about Hofmann products, which are the less substituted products formed by elimination. And I did a little summary of that down here. Again, you could make the Zaitsev product or the Hofmann product. Well, in this section, we discuss Hofmann elimination. And we said, well, you can do that with an amine as well. And how would you do that? What you do is you take your amine, you treat it with excess methyl iodide, you end up completely exhaustively alkylating it, and then you convert the amine to a good leaving group. Okay, what's the next step? The next step is to treat it with silver oxide, water, and heat. That's kind of just steps you need to memorize. But what that does is that it exchanges the iodide ion for a hydroxide ion, and then you just do the E2 elimination. And then we discussed the mechanism, okay? We discussed the mechanism of the E2 elimination, which is not much of a surprise to us, but we have another beta hydrogen over here. Oops, I'll use my blue pen. And, you know, we always want to answer the question, why do we pull this proton off to make the Hofmann alkene as opposed to the blue proton off to make the Zaitsev alkene? And we said, if you look at the Newman projection of the two possible eliminations, if you were to rip off one of these protons here, you end up with this group over here and the nitrogen with the three methyl groups on it. You see that you have an unfavorable gauche interaction here. Whereas if you make the Hofmann product, you see that you don't have that gauche interaction. It's not there. And that's the answer. That's all there is to it. Okay, nothing more than that. And so after that, we answered a couple of questions about Hofmann elimination, and that brings us to the next section. So that was the little review I wanted to do before we get into the next section, which deals with reactions with amines in nitrous acid. Nitric acid. Everybody knows what nitric acid is, right? That's HNO3. So this is nitric acid. And what happens when you lose an oxygen? You go from nitric acid to nitrous acid. So HNO2 is nitrous acid, and you need to know the structure of nitrous acid. And the thing is that nitrous acid is actually unstable. Okay, you're never going to walk into a lab. You know, if you think about all the labs that you've done, if you've done any wet labs, and I'm sure you all have, if you think about walking in the lab, you'll never find a bottle of nitrous acid. Why? Because it's so unstable. It has to be generated how? In situ. There's that phrase coming up again. It's Latin, and it simply means all in the same flask. So how do you make nitrous acid? You actually combine sodium nitrite and HCl. Okay, so in order to make nitrous acid, you combine sodium nitrite, okay, the Lewis structure of which is shown here, and then you combine it with HCl, okay? And what happens is you do a proton transfer followed by, you do a proton transfer to make nitrous acid. But again, nitrous acid is unstable, okay? And so it undergoes another proton transfer and loss of water as a leaving group to make this cool ion, which is a nitrosonium ion. Okay, so not only do you need to know what a nitronium ion is, right? We learned about that when we talked about nitration. So now you've got the nitrosonium ion. So the nitronium ion and the nitrosonium. If you remember, the nitronium ion looks like this. It's where we have, you know, this like this. This is a nitronium ion. So that's not what we're talking about right now. So maybe I'll delete that. But that was something that was different. And now we're talking about the nitrosonium ion, and you can see that it's got two resonance structures, and it is going to be a very powerful electrophile with that positive charge on it that you see down there. So a very powerful electrophile, the nitrosonium ion. Now, if you're wondering, okay, great, I made this very powerful electrophile. I have it on the next slide here. What would I do with that? Well, again, since it's so electrophilic, okay, it's going to immediately react with an amine as soon as it forms. So if you have any amine in your reaction mixture, if you generate the nitrous acid in situ, it makes the nitrosonium ion, and then your nucleophile is going to react with it. If you take a look at these two resonance structures, I'm going to ask you a question about this. If I call the first one A, and I call the next one B, could anybody tell me which one of these would probably contribute more to the resonance hybrid overall, or just maybe even make a guess? Yeah, I see a lot of students are saying A, and I think the rationale there is usually that they're thinking, well, oxygen is more electronegative than nitrogen, and so the nitrogen is going to be more comfortable with the positive charge, but in fact it would be B, and the reason why is because in B, everything has a complete octet. Right? If you look at the nitrogen here, it has 1, 2, 3, 4, 5, 6 electrons surrounding it. The oxygen has an octet, whereas in this resonance structure, everything has a complete octet. And so normally when we draw the nitrosonium ion in a mechanism, I mean, usually the author of this textbook, I think, uses both, okay? And he probably uses this. But a lot of times if you talk to a professional chemist, most of the time they'll draw it like that. But again, it's neither here nor there. It's not going to change your life. Now, you want to talk about reactions that aren't all that useful in organic chemistry? I'd say that this page kind of sums one up here. If you take a secondary amine, so this is a secondary amine, and you treat it with the nitrosonium ion, well, how do you form the nitrosonium ion? You form it by combining sodium nitrite and HCl, which makes nitrous acid. That loses water to make the nitrosonium ion, right, which is shown right here. Okay, well, the secondary amine can do a nucleophilic attack. Of course, it's showing it on the least, or the resonance contributor that contributes least to the resonance hybrid, whatever. Anyhow, we do the nucleophilic attack in a proton transfer, and we end up with this wacky new functional group that you see down here on the bottom right of your screen, and that's called a nitrosamine, or an N-nitrosamine is the correct term. Now, if you're wondering, why did you say this is like kind of a useless reaction? Well, there's nothing that's useless. I'm sure it has its uses in organic chemistry, but generally speaking, we don't think of nitrosamines as being, good drug candidates because they're known to be potent carcinogens. For example, if you look at these compounds here, you see this N-nitrosodimethylamine. So you just take dimethylamine, which is a secondary amine, you treat it with nitrous acid, which is produced from sodium nitrate and HCl. You end up with this compound, which is found in things like cold cuts and beer, whatever. Then you have this one here, which comes from pyrrolidine, and that's found in things like bacon. And then you have this one, which is basically just you add a nitroso to nicotine, and that's found in tobacco smoke. But again, all of these compounds are essentially poisonous to some degree. And so we don't think of nitrosamines as being the most useful compounds in the world. However, if you take a primary amine and you do the same thing, then we get something very, very different. And it's actually very cool reaction. And it does a process called diazotization. Let me show you what I mean. What you do is you start it with a primary amine. You treat it with the nitrosonium ion, which again, you can't buy a nitrosonium ion. You can't buy nitrous acid, but you make it from sodium nitrite and hydrochloric acid, and you end up with a diazonium salt. Okay? Now, a diazonium salt, I'll put in all the lone pairs here. There's a lone pair on the nitrogen, and there's 4 lone pairs on the chloride. But the diazonium salts are very useful in organic chemistry, depending on what the R group is. And let me explain what I mean by that. First, let's take a look at the mechanism. So you form your nitrosonium ion. You have the primary amine that attacks. You do a couple of proton transfers, and you end up with this really interesting intermediate here. You essentially lose another molecule of water after another proton transfer, um, and you end up with your diazonium. Okay, so this is the diazonium. And normally, well, not normally, but a lot of times I would say that diazoniums are drawn like this without the anion being shown at all. So the chloride is left out. Let me show you an example right here. So here's an example where they left the chloride out. So let me show you. It says alkyl diazonium. Okay, so if you have like a butyl diazonium or a propyl diazonium salt, those are actually pretty explosive. And generally speaking, in chemistry, we frown upon reactions that produce explosions. We don't want to do explosions. We don't want things to blow up on us. So that's not very useful. But here's something that's extremely useful. And these are aryl diazonium salts. Okay, so if you take aniline or some derivative of aniline, right? Aniline is a primary amine, okay? You treat it with the nitrosonium ion, which is, again, produced from sodium nitrite and HCl in situ. You end up with the diazonium salt. Yes, I know that the chloride is here. Again, in organic chemistry, organic chemists are obsessed with leaving counterions out, but you end up with the diazonium salt. So that's this right here, okay? And then there's all kinds of cool chemistry that you can use to substitute different functionalities where the diazonium is situated on the ring. And the names of those reactions, they're called the Sandmeyer reactions. I worked with a guy who was cursed when it came to the Sandmeyer reactions. We had a discussion, I worked with a guy for many years, and I said, is there anything you can't get to work in the lab? And he said, I'm pretty bad at Sandmeyer chemistry. He said, whenever I try it never works. But in the hands of most organic chemists, it does work really well. So what you do is you take your diazonium salt, okay, and you react it with a copper 1 salt. So copper 1 bromide, copper 1 chloride, copper 1 iodide. And what that does is it just substitutes the diazo portion for a bromide, a chloride, or an iodide, respectively. Then there's another one. You can treat it with cuprous cyanide, which is copper 1 cyanide, and you can insert a nitrile. So you make this compound, which is called benzonitrile, and we looked at the nomenclature of carboxylic acid derivatives earlier on. So this is benzonitrile. But what's cool about benzonitrile is this, and I know there's not a lot of space here, is that if you treat this with aqueous acid and you cook it up, then what do you get? Benzoic acid. So that's another new and exciting way of making benzoic acid. And we saw how useful carboxylic acids can be in organic chemistry. So let me show you a cool reaction sequence here. It says overall, the Sandmeyer reaction is part of a multi-step sequence to install a carboxyl group on a benzene ring. All right, let's take a look at what's going on here. Is first we have the nitration, right? This is again from chapter 18. Remember that when we take an aromatic ring and this molecule here, I've brought it up several times over the course of the summer. This is called cumene. You take cumene, you treat it with nitric acid and sulfuric acid. What do you end up doing? You end up putting a nitro group there. Okay, after you do that, you reduce it. So when you do the reduction, first you treat it with iron and aqueous acid, followed by treatment with sodium hydroxide. So this is the reduction. Okay, the reduction. That would give you the aniline derivative. So that would be what? Para-isopropyl aniline is what you'd end up with. And then in the next step, you're doing the diazotization. So that's what it's called, diazotization. And that's going to form this, the diazonium salt. So this is a diazonium salt. Then we treat it with cuprous cyanide, which is copper 1 cyanide. This is a Sandmeyer reaction. So Sandmeyer, and there's several Sandmeyer reactions, but this is one of them. Sandmeyer reaction. And then in the last step, you're doing the hydrolysis. So this is hydrolysis, okay, to convert the nitrile into the carboxylic acid. So there you go. And if you think about it, are there other ways of installing the carboxyl group? Yeah, probably. We have other ways to do it. We could do a bromination, and then maybe try a Grignard or something like this. But this would be a very effective way of doing this chemistry. All right, a couple more reactions, which are just kind of like, I don't know, one-offs, so to speak, that just show up in the textbook towards the end. Is this one here? Is you can take the diazonium ion and you can treat it with fluoroboric acid. So this is called, let me see here, fluoroboric acid, like this. And this reaction actually has a name. I don't know if it's mentioned in the book until the end, but this is called the CHEM reaction. CHEM reaction, which is where you take the diazonium ion and you convert it into you replace it with a fluorine. And if you think about that, you can't do that with Sandmeyer chemistry. And so it's an actual, it's actually an extremely useful reaction, the CHEM reaction. And the last one, or sorry, the next one is where we just replace the diazonium ion with a hydroxyl. And to do that, we just treat it with water and cook it up. Okay, so a couple new reactions here. And if you think about it, we don't have many ways in our class to install fluorines. I don't think we have any way yet. And we don't have many ways to install a hydroxyl, right? Things like an SNAR maybe, but those require very specific conditions. So there you go. All right. The last kind of reaction that we learn in this chapter that for which you use a diazonium ion and you're not making a diazo compound anyhow, is to use this acid. So this is called hypophosphorus acid. So hypophosphorus acid, H3PO2. And using H3PO2, you can convert the diazonium ion, just replace it with a proton. Okay, so essentially it's a way of converting an amine, right, that's attached to an aromatic ring into a proton. So let's take a look at this reaction sequence here. It says this is useful when the amino group is required on a ring, right? How would we add 3 bromines to an aromatic ring? Well, the only way that we know how to do that would be to polybrominate aniline, right? So if we first did the nitration, okay, in the first step, then the reduction, we end up with aniline. We treat that with bromine, and we end up with the polybrominated compound. But then we can remove this by first doing the diazotization, so the diazotization, and then we treat it with hypophosphorus acid. So anyhow, which we see up on the top of the slide, hypophosphorus acid. So if you think about it, again, it's one of those things where we would have no way to really make this compound without having the diazotization. Again, you think about it, if you're thinking, well, couldn't I just do bromination after bromination after bromination? No. Why? Because bromine is an ortho-para director and everything here is meta, and it's also weakly deactivating. So that's something else to consider. Very difficult thing to do without that strategy. So you notice that I chose my words carefully on the last slide, and I said, this is the last reaction except for making diazo compounds. So diazonium salts, right, since they have that positive charge on them here, they also make really good electrophiles, provided they're in the company of a good nucleophile. So if you put a diazonium salt from an aromatic ring near another aromatic compound that can serve as a good nucleophile, so meaning it's got to have some kind of electron donating group. So here we have a electron donating group, so we'll put EDG, or EDG, or you can say it's activated, it's very highly activated. Well, that can act as a nucleophile, can't it? Right? That can act as a nucleophile, and you end up making a sigma complex. Remember chapter 18? Here's the sigma complex coming back at you, right? So you make this really interesting sigma complex, you do a deprotonation, and you end up with what we call a diazo compound. So this is called a diazo compound, okay? And this process, the whole thing that you're seeing on this page, it's called azo coupling, okay? So if you're like, what's azo coupling again? Let me tell you. Azo coupling is when you take an aryl diazonium salt and you combine it with another aromatic compound that has an electron donating group on it, something that's going to act as a good nucleophile, okay? So that's what azo coupling is. And if you're wondering, what the heck's the point of azo coupling? What's so great about that? Well, Azo coupling is actually used to make what are called Azo dyes. And if you read all the different asides in our textbook, you probably noticed that in chapter 18, there was a blurb about the fruity pebbles. I think it's chapter 18 where they talk about the fruity pebbles and the dyes that are used. And I'm not kidding, the dyes that they use to make the bright colors of the different fruity pebbles. Well, those come from diazo compounds. And so the diazo compounds, the reason that they're colored or have different colors is because they're all conjugated, single, double, single, double, single, double, single, double, right? The whole system is conjugated. And so it absorbs light so that we can see all these different brilliant colors and the variations of substitutions on the rings, like depending on where you have substitution, you get different colors. So that's what diazo compounds are for. And in fact, if you look at the ingredients of some foods, they have dyes in them. Sometimes it'll say, azo compound this or azo compound that, So anyhow, that covers everything in section 20.11. There's some practice problems that I want to look at, and they require quite a bit of room. So I'm going to switch over to a blank document. Just give me 2 shakes of a lamb's tail here. Find some space. And we're going to give this one a shot. So I'm down in the bottom of the barrel here. So we're going to try, this is question 22.26. And this is question B. So we're starting with nitrobenzene. So you can see right away, this is a good candidate for diazotization. We're taking nitrobenzene and we want to convert it to this 1,3-dibromobenzene. So the 2 bromines are meta-substituted. And so there's no way that I can put 1 bromine on and then just add another, can I? Because bromine is an ortho-para director, isn't it? However, if I think about diazotization, right? If I step backwards and I think, well, what if I had the diazonium salt? Okay. If I had the diazonium salt, or the diazonium ion, whatever you want to call it. I'm just not calling it the salt, I guess, because I'm leaving the chloride out. You can call it this an diazonium ion or the diazonium salt, whatever. If you want to put the chloride in, go for it. I'm not sure if he does or not in the textbook, but it's neither here nor there. But we know that the diazonium ion comes from this compound, right? We have to have the aniline derivative, okay? Right? And we know that this is going to come from the nitro. And we know that nitro is a meta-director, isn't it? Right? So then the question becomes, how do I get from here to here? Well, that's not all that difficult. Right? If I have nitrobenzene, all I have to do is treat it with bromine and a Lewis acid like iron 3 bromide, and that's going to brominate in the meta position because nitro is strongly deactivating. And so anything that's strongly deactivating, except for the halogens, is going to direct to the meta position. Okay, so now all it is a matter of making the diazonium ion and then using Sandmeyer chemistry. So how do I make the diazonium ion? Well, let's recall. The first thing we're going to do is we're going to reduce this. Right, so I would reduce this in the first step using iron or zinc and aqueous acid. That would give me the ammonium ion. So I want to deprotonate that. So I'll use sodium hydroxide in the second step, and that will give me 3-bromoaniline. That gives me this compound. Now I'm all set up to treat this with the nitrosonium ion to make the diazonium salt. How do I do that? I take this compound and I treat it with sodium nitrite and hydrochloric acid together, and I make my diazonium ion. Oftentimes in the book, he just writes it like this, N2 plus, like that, which is totally fine. And then to replace the diazonium ion with a bromine, all I do is a Sandmeyer reaction. So I treat it with copper 1 bromide. So this is a Sandmeyer reaction, this last one here. There you go. So now we've got 2 bromines installed on the ring, and they're meta to each other. So that's kind of interesting. You know, it's something that we wouldn't have been able to do without Sandmeyer chemistry. And in order to do Sandmeyer chemistry, you have to make a diazonium ion. You can't do Sandmeyer chemistry without it. It's impossible. So there you go. You got to master Sandmeyer chemistry and organic chemistry too. It's really, really helpful. Well, let's move on to the next one. So this is 22.26 C. So we're starting it with benzene like this. Okay, we're taking that and we're going to treat it so that we put a hydroxyl in here, and we have this propyl. So I want metapropylphenol would be the name of this compound. But how many ways do we have to make phenols really in organic chemistry, right? If you go back in your notes, and I'm not going to switch back to the slides right now, but we saw earlier today, just a few minutes ago, that if you take a diazonium ion, okay, like this, and you just treat it with heat or water and heat it up, is what I'm trying to say, what you end up with in that case is a phenol. So a hydroxyl is an ortho pair director, as is an alkyl group. So, you know, I mean, this doesn't get us really all that much further unless we use Sandmeyer chemistry again. So that's going to be our best strategy, would be to use the Sandmeyer chemistry. So in terms of retrosynthesis, what I want to think about, and I'll use my red pen here, is that I want to end up with this compound. Here's my diazonium ion. Kind of running out of space there, so I'll put my propyl group like that. Now, how am I going to make this compound? And you see I'm doing a few more retrosynthetic steps than I normally do, aren't I? Right, I'm taking a few steps back here. So I know that I'm going to make this from this compound, okay, where I have the nitro here, and I've got my propyl group here, like this. Well, the thing is, I know that a nitro group is deactivating, and another thing that I know is that there's only one way for me to install this propyl, right? And I know that the propyl must have to be installed by a Friedel-Crafts acylation. So that means that my precursor is actually going to be this, and then I'll reduce the carbonyl off using a Clemmensen reduction, okay? So, you know, I've got these two groups. This is a meta-director, right? That's a meta-director, and this is a meta-director. Well, since this one is more strongly deactivating, what I'm going to do is I'm going to install this one first, okay? Because it's simply less deactivating. So this is a strong deactivator, and then this one is a moderate deactivator. So moderate deactivator. So there we go. So we're going to install the acyl group first. How do we do that? We use Friedel-Crafts acylation. So we're going to take our benzene and we're going to treat it with propanoyl chloride and aluminum chloride, or Lewis acid. And that's going to install our acyl group. So let's draw that in. Remember, this is a meta-director. So you might be thinking, well, I need to reduce this, right? I need to reduce this with the Clemmensen reduction immediately. No, because you need to have a meta-director in order to put that nitro group in the correct spot. So I'm going to treat this with nitric acid and sulfuric acid. And that's going to give me this compound where I have my nitro in the right spot, like this. And I actually made a note to myself here in my notes that I have in my desk here. And this is something that they brought up in the textbook that I made a note of, is now if we try to do the Clemmensen reduction, so this is the Clemmensen reduction, which is you treat it with the zinc and mercury amalgam, and you throw some hydrochloric acid at it and heat it up. It says here that that's actually going to reduce both the carbonyl, but it's also going to reduce the nitro, right? If you think about nitro reduction conditions, right, using a metal and an acid, like in the last question, what did we use? We used iron and acid. Well, here we're using zinc and acid. So since there's zinc in the zinc mercury amalgam, it will do both reductions. If you did them stepwise, it wouldn't matter. Okay, I wouldn't care at all. Either way, you're going to get the right answer and you understand what the heck is going on. But we're just going to, do these 2 steps in one because all organic chemists, organic chemists love to do 2 steps in one whenever they can. Now we need to do the diazotization. So we're going to treat it after we wash it with base, of course, because we'd end up with the aniline. But then we're going to do the diazotization. So we treat it with sodium nitrite and hydrochloric acid together. And we're going to end up with the diazonium ion. So let's draw that in. This time I'll draw the little structure here. And then the last thing to make the phenol is we just treat it with water and we heat it up. And there you go. That's it. But again, this is the kind of synthesis that the only way to get through to the end of this is to know your chemistry with diazonium ions, right? The reactions with the copper 1 chloride, copper 1 bromide, copper 1 iodide, and the copper 1 cyanide, those are the Sandmeyer reactions. The other ones aren't, like this isn't a Sandmeyer reaction. It's just a reaction with a diazonium ion. But anyhow, you need to know your diazonium chemistry. Let's try one more, and I'm running out of space here, so